Okay, I'm giving this presentation on behalf also of the 259 individuals, scientists around the world, who have contributed in a great deal to this report by leading a chapter, being a lead author, being a reviewer, or a review editor. But in addition to the 259 authors, we have over 800 contributing authors. These contributing authors are the fine fabric of the root system into the scientific community. And it is very important to base our scientific assessment on a much broader foundation than just provided by the lead authors coordinating lead authors. I should also say with great pleasure and deep acknowledgement that from this country, of the 259 authors, 29 hold the affiliation of the United Kingdom, which means that this country has contributed over proportionally to the scientific assessment, and we're all very grateful for that. And somehow, yes, now it works. So our assessment consists of 14 chapters, an atlas, overall more than 1 million words, and obviously nobody is reading 1 million words from back to back. That's why, per mandate, we also summarize it. We summarize it in a first step into a technical summary, and then into a summary for policymakers. The summary for policymakers, as you know, is negotiated. It is discussed word by word during a 4-day meeting that took place in September 2013. One of the most frequent criticisms that we had to receive over the production phase of our assessment was that the summary for policymakers still tend to be too technical, too long, and hard to communicate. And that is why, for the first time, we decided in Working Group 1 to provide one more distillation step from this comprehensive report into what turned out to be 19 headline statements. These 19 headline statements provide a coherent narrative of the entire Working Group 1 report, and they print on less than 2 pages. So there is no excuse anymore for a policymaker not to understand what we have found, nor not to have time to read what we have found. I will base my presentation on the 3 major streams on which we organize our assessment. That of observation, understanding, and the most important one, the projection of climate change. Here you see the changes in surface air temperature as they are measured and available from millions of measurements for the past 112 years. And we see that the warming is widespread on this planet. We also see that there are glaring gaps of knowledge and quantification of the changes of climate, in particular in the southern hemisphere, but also on specific areas of continents. We were very clear that we wanted to communicate these gaps also at the highest level in the summary for policymakers. This, together with many other observations, led us to assert that warming in the climate system is unequivocal. And you remember that this was a sentence that was already expressed in the 4th assessment report. For us, it was important to restate this important finding of the 4th assessment report published in 2007, and to therefore provide a historical thread back to what the scientists have been doing and finding in the previous reports. This time series does not occur in the assessment report, but I have the privilege still as a keynote speaker here to show it, because it is providing the paleoclimatic context of the carbon dioxide concentrations in the atmosphere, and because this time series is very close to my heart. You see here the changes of carbon dioxide as measured in the Antarctic ice core record that was drilled under the umbrella of the EPICA project, reconstructing a greenhouse gas history of the past 800,000 years, spanning 8 full glacial interglacial cycles. And you see, CO2 has always varied in the climate system. But what we are observing today is unprecedented in the past 800,000 years, with concentrations exceeding 400 ppm for the first time in 2013. And it's actually a very robust prediction to say that in 2014 onwards, we will see these numbers of concentrations that start with a 4. These concentrations are 30% higher than anything that we have measured in this ice core, and therefore these concentrations are unprecedented in the last 800,000 years. We could make similar observations with methane and nitrous oxides, together the 3 most important greenhouse gases after water vapor. This figure also is from deep within the report, but I come to love it because it's a fingerprint of how man has changed the climate system from a very fundamental physical point of view. It shows the change in energy content in the major compartments and components of the climate system. What you see in blue is the increase of energy content in the surface ocean. The lighter blue, top 700 meters. The darker blue, the layers below 700 meters to 2,000 meters. These are observations and measurements that are, again, made possible through a concerted effort of the world scientific community, in particular the physical oceanographers who have sent autonomous floats around the world ocean that register temperature, salinity, and pressure, and permit us to calculate the change in the energy content. You see these curves go up. The ocean renders us with the service of integrating the climate signal. The energy has increased in total by about 250 times 10 to the 21 joules. And the 3 small slivers of white, brown, and red colors indicate the increase of energy by the cryosphere, by the soil, and by the atmosphere. In a way, it's paradoxical. We always talk about surface air temperature and their changes, sometimes even on a decadal basis, when it is the ocean that provides us with a time-integrated measure of anthropogenic climate change, which itself, I would argue, is unequivocal. What was also a progress in Working Group 1 was that we could close the energy budget, thanks to measurements of that sort. A second important budget could be closed, again, thanks to satellite measurements that inform us about the mass losses of Greenland and Antarctica, plus estimates of losses of glacier mass over the past few decades. It concerns the sea level budget, an important quantity when it comes to climate change, important because this forms the basis of our confidence for projections which, for the first time for sea level, could be made in a comprehensive manner, including all the contributors to sea level. Let me now proceed to the second pillar of our understanding, another figure that indicates quantitatively that we know why climate has been changing on the variable of global mean temperature over the past 60 years. The observed increase in global mean temperature you see as the black bar on the top between 0.6 and 0.7 degrees Celsius. There are various drivers in the climate system, all of which are assessed in specific chapters. The greenhouse gases actually provide more drive than is necessary to observe and explain the increase in global mean air temperature. That is because we also have drivers that provide a cooling in the climate system. It is the sum of all the aerosols that provide a cooling on the order of about 0.25 degrees Celsius. Each of these drivers are associated with uncertainties which are quantified in this figure. But the important point here is that the sum of the positive and negative anthropogenic drivers matches the observed temperature changes over the past 60 years. In turn, solar and volcanic variability, as well as internal variability in the climate system, are unable to quantitatively make a sizable contribution to the temperature changes that we observe in the past 60 years. And that is why we say it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. But there is more in this area of detection and attribution. That is the quantitative link between cause and effect. Cause being the increase of carbon dioxide in the atmosphere through the burning of fossil fuel and deforestation. The effects being felt and measured worldwide. And we assembled in our chapter quite a large range across all climate system components. The warming of the atmosphere, the land and the ocean, the changes in statistic of some extreme events, the changes of the water cycle on very large scales, the retreat of sea ice, the melting of glaciers, and the mass loss of ice sheets. And finally, the largest integrator on this planet, global mean sea level, which has risen by 19 centimeters in the past 112 years. All of these scientific findings have led us to what is the simplest of all these headline statements in our summary for policymakers, and it simply affirms human influence on the climate system is clear. The power of such a headline statement is not only that it is short and concise, but that all the governments of the world have actually approved this very sentence. Let me now move to the future. There's a huge effort of the scientific community, and this community has been very heavily involved in that as well as in the other efforts, to project climate change over the next 100 years and beyond in terms of changes in temperature, changes in all variables in the climate system. Here I just show you the most important metric, if you wish, global mean temperature change as simulated by these models of over 25 centers across the world. But you will hear more about that in one of the following presentations. You see, for simplicity, we highlight just two scenarios. Here, a business as usual scenario in red and a strong mitigation scenario in blue, with the red scenario showing increases in global mean surface temperature exceeding 4 degrees by the end of the 21st century, while temperatures have been stabilized in the mitigation scenario. We render this figure and these results into a policy-relevant statement at the level of the headlines by saying that global surface temperature change for the end of the 21st century is likely to exceed 1.5 degrees Celsius relative to 1850 to 1900 for all scenarios except 2.6. We rendered this because the 1.5 degrees Celsius is one of the targets mentioned in the UN Framework Convention on Climate Change. And so we actually make that step in IPCC to not only report on our findings, but also cast them in a way that is relevant for the policymakers. What is also relevant for the policymakers and the user community is this atlas of global and regional climate change. An atlas that is free of charge, available for everybody around the world. You can analyze your own region. The scientists have assembled 35 regions around the world, extracted the data from all the climate model simulations that were available for this assessment through the Coordinated Model Intercomparison Project, and show that for two variables, temperature increase and precipitation change for these regions. Another very important and policy relevant concept was put forward by Working Group 1, and we're yet to see the effect of this. It concerns one of the new metrics by which we account for the changes in the climate system in the future in response to our activities now. It is not climate sensitivity that has been so much in the media in the past, but a more, what I argue, relevant metric that connects the physical changes to the carbon cycle. It's the transient climate response on cumulative carbon emissions, and it is a number that derives from the insight that the cumulative emissions of carbon dioxide since industrialization are linearly related to the global mean warming in the 21st century. And in fact, we can quantify that every 1,000 billion tons of carbon would cause a warming between 0.8 and 2.5 degrees Celsius. So this then is the basis of a very policy-relevant insight that says that if the policymakers agree on a climate target, the moment that happens, this moment we can provide the number for the budget of carbon that can be emitted since industrialization into the atmosphere. So the notion of a limited carbon budget has now been inserted also here in the process of IPCC. And somehow this guy is no longer responding. Okay, I'll move over here. Now, this is basically what is shown in this last figure of the summary for policymakers, which you see on the horizontal, the cumulative total carbon emissions, and in the vertical axis, the warming in the 21st century relative to the early industrial period. You see that all the scenarios basically lie on one line, irrespective of the specific scenario. The only point you can distinguish between the scenario is when they reach the year 2100. In addition, we also give uncertainties estimated from various model simulations and other considerations. They are indicated by these colored wedges. Now, for a policymaker, this figure can now be used to get a first estimate what it means to reach a 2-degree target. For example, you can read off that the cumulative carbon budget associated and consistent with that target is 790 billion tons of carbon. And that then may lead you to a very simple consideration of looking at what we have available and what we have actually emitted already by the year 2013. 535 billion tons of carbon. And it's very simple, back of the envelope, to take the difference, 255, put that in context with what we have emitted in 2013. And you see, this is the way the natural scientists, the physical science basis, communicates the urgency of the problem. At current emission levels, we would have exhausted the cumulative carbon budget in the next 25 years. And that is how we can make this other headline statements towards the end of our summary for policymakers. Limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. That again is a statement all governments have agreed. So here we have, in short, the narrative of our assessment of the physical science basis. We tried to cast these very complex scientific findings based on more than 9,200 peer-reviewed studies published essentially after the previous assessment report into some very simple, precise, concise, and quotable statements. But let me now come to the last part of this presentation. As you appreciate, our assessment has been delivered in September 2013. And so there has been some time to reflect on what could be better, what at least are the challenges as we think further in the future. And that's the opportunity here at this conference to do so. Well, first of all, logistical challenges. I will come to the scientific challenges after that. I think we have seen in the example of precipitation measurements, and the governments have been quite explicit to want that information also at the level of the summary for policymaker by including an additional figure at the approval plenary, speaking to changes in precipitation. And that means that there is a continuing challenge of maintaining and also upgrading high quality and high density observation networks. We also have found our limits when it comes to access and manage the massive amounts of numerical data from all these climate simulations that have been carried out by over 20 centers around the world, producing over 2 million gigabytes of numerical data. It's a huge amount, and yet we had to analyze it because that was the heart of the quantification of climate projection. There are further challenges around the corner. The physical science basis of climate research is rather well organized. There is a new program arising, Future Earth, and it is important, I think it is chiefly important to have good relationships between two programs, between the physical science basis and Future Earth. In fact, there should be a merger here where we are able to bring in our quantitative results into the many other questions that are on the focus and the radar screen of Future Earth. And I can assure you that this scientific community is very ready to deliver. Climate research in the regions. I've mentioned to you the Atlas. The Atlas is becoming quite a popular product because it speaks to the people in the regions. But at the same time, we also appreciate the limits of this Atlas in terms of the resolution of the simulations, in terms of the uncertainties, in terms of the variables that we were able to deliver to people in regions. And there is a lot to be done here to bring this science to these regions. And I may say we have talked about capacity building in IPCC over the past 25 years, but there is still a long way to go. So these are these 3 reports that are out now, and I would say these reports and the entire IPCC activity since 1988 has catalyzed all these scientific communities in a fantastic and tremendous way. But we also have realized the limitations of what voluntary contribution of scientists can do and can achieve. And therefore, I plead to the decision makers to think hard about increasing the institutional support of scientific assessment work. Let me now come to the scientific challenges. The regional modeling I've already mentioned in passing, but I think it's the water cycle that I would like to see much more progress on. But you also can put together something that I said earlier. We cannot make tangible progress if we have gaps in the observational system, something that also has been identified in our assessment. Extreme events have been featured in a special report in the 5th assessment cycle, and that as well has many open questions. It's so important because it's one of the amalgamating processes and issues between the working groups, and therefore I think the physical science basis here can contribute a lot, but we still have a long way to go. It was one of the early ideas in the 5th assessment report to have a chapter on detection and attribution. Of course, we need to have that, but in that chapter to go from global to regional. I think we have gone ways, and Peter will probably mention that, but we didn't go as far as would be necessary for everybody on this planet to say, what I have experienced in terms of changes can be attributed to a global cause. I think it's increasingly important to also bring the regional aspects of detection and attribution out into the world. Spatial quantification of vulnerability and exposure. I'm sure we will hear much more about this from Chris Field. I would love to see maps of vulnerability for certain variables. I would love to see maps of exposures and then bring them together with maps of changes in some statistical aspects of physical variables. That would be a true integration of these different approaches. And finally, that is a word to Working Group 3. I think everybody talks about this, to bring together economic models with the physical models in a truly coupled way. But I think there are still large hurdles there, hurdles of understanding the individual research communities, but also hurdles in terms of the mathematical approach, how these models work. We in the physical sciences have a time marching approach, whereas many of the economic models still look at entire paths over the 21st century and solve their models with completely different mathematical approaches, which makes it very difficult to actually come together on that basis. Let me come to the last slide here. I much appreciate the value we get out of the modeling intercomparison projects, which by now have become standard in the physical climate science community. These efforts carve out a lot of computer time, I'm aware, of the big centers. But it's not only for IPCC work. The scientific community is using these simulations to learn more about modes of variability, for example, about sensitivities in the climate system, etc. So it has a lot of benefits for the scientific community once these numerical data are available broadly. And that is why I think we should proceed now and further develop what has started in some nuclei in specific regions, so-called regional model intercomparison projects. That's something that could happen between working groups 1 and 2. I invented a new acronym here, VXMIP. That's the Modeling Intercomparison Project for Vulnerability and Exposure. I've no idea whether the scientific community is ready for such a thing, but I know that Working Group 2 would be called here on the floor. And an EMIP, an Economic Modeling Intercomparison Project, would also be quite useful for the communities to come together and really compare their results. And that is something that I've seen emerging from Working Group 3, but Working Group 1 can contribute here as well. We had very intensive debates about scenarios and climate targets, and that is a typical area where these economic models would come in as well. And my final word here, after all, IPCC, institutions, logistics, etc., the heart of the science is the curiosity-driven science. And it cannot be said often enough, because as a reviewer of a research project, often I stumble upon sentences like, we propose this work because it's so important for IPCC. That's when I start thinking, oh, is that the only reason why you're motivated to do that? No, please continue to support and increase the funding to curiosity-driven research, because it's most of the time the good ideas come from there, and then you can proceed with the future assessments. So thank you very much for your attention, and I'm looking forward to the interaction with you. Thank you.